Hi, everyone. This video is an opportunity for us to take a look at a function known as the exponential function. Now, the form of an exponential function looks like this: y equals a times b raised to the x. But to keep things simple, I'm just going to back up here, and I'm just going to go y is equal to 2 raised to the x. Okay, this is what the graph looks like. It's this curve. And as you can see, it sort of, as you move to the left, it kind of veers towards the x-axis, and it even looks like it actually touches it. But if I were to zoom in, you can see that it's not touching, and it's actually just slightly above the x-axis. And I'm just going to go over to the left. Oh, it looks like it's touching again, but if I zoom in even closer, again, it is just slightly above the x-axis. So in fact, this graph never actually touches the x-axis. Okay, it zooms towards it as you move to the left, but definitely does not touch. Okay, as you go to the right, it just increases without bound towards infinity. Okay, so we can say that the domain of this function would be y is an element of, or sorry, x is an element of the reals, and for the range, we would say y is greater than 0. We can't say y is greater than or equal to 0 because, again, it doesn't actually touch the x-axis. All right, so let's play around with some other aspects of this. Take a look at the y-intercept. Okay, the y-intercept here is 1. Okay, now there's nothing about this function that seems to indicate to us explicitly that the y-intercept is 1, but watch this. If I were to keep y is equal to 2 raised to the x, but I were to put a number in front of it, like let's say 3 times 2 raised to the x, now you get this blue curve. It's still basically the same shape as the exponential function. It still is an exponential function, but now it has got a y-intercept of 3. Now that's kind of interesting, you might think, because 3 is precisely the number that I added in here at the beginning, what I multiplied the exponential function 2 to the x by. Now, similarly, you might say, well, maybe there is a 1 here. Maybe it was 1 times 2 to the x, right? And because it's 1 times 2 to the x, maybe that's why we have a y-intercept of 1. Well, let's test this out, and let's go y is equal to maybe 4.5 times 2 raised to the x. Okay, now if you look at this, the y-intercept there is in fact 4.5. So one thing that you know is that this number in front that's multiplied by the power in the exponential function is precisely the y-intercept. Okay, let's take a look at a couple of other things. So I'm going to go back to plain old y equals 2 to the x. I don't need the 1 times because it's redundant. And now I'm going to go y is equal to 3 raised to the x. Well, y equals 3 to the x is this purple graph, and it looks basically, it has basically the same shape. But now if I were to add y equals 5 to the x, so essentially what I'm doing is I'm increasing the base of the power. It looks like it's turning a little bit more sharply or increasing at a more rapid rate. Okay, and in fact, that is exactly what's happening. If I were to go y is equal to 20 raised to the x, that would be, right, even more of a sharp increase. Okay, good. I'm going to take a look at some other things here. What happens if you have, instead of 2 or 3 or 5 or 10, you have a number for this base that is between 0 and 1. So let's start with half. Okay. Oh, this is not the way to do it. Let me type this in again. I might have to just delete the whole thing. Y is equal to half raised to the x. Okay, so half, excuse me, is a value that is between 0 and 1. So you see, we do actually have sort of the same curve as we saw before, but it's kind of been flipped. This looks like the mirror image. So what's happened here is now, as we move to the right, the graph gets closer and closer to 0, but never actually touches. And as we move to the left, it increases without bound. Now, recall what y equals 2 to the x looks like, or looked like. You might notice some kind of a relationship. Let's try another one. What if we went with y is equal to 1, dare I do it, 1/10 to the x? Okay, so that's that green one. But now what if I were to graph y equals 10 raised to the x? Okay, so you get this purple one. So let me just turn these off so that it's not too busy. So the green one is y equals 1/10 to the x, and the purple one is y equals 10 to the x. Both of them have a domain that is common. X is an element of the reals. Both of them have the same range. Y is greater than 0. Both of them happen to have the same y-intercept, which in this case is 1. So all of the properties are the same, but we could say that the purple one is increasing, right? Whereas the green one is decreasing. And that does, in fact, have something to do with the base value here. Okay, so a few things to think about there. But there it is. That is the exponential function y equals a times b to the x. Now, for further investigation, what you might want to do is to go to desmos.com, start graphing, and type in y equals a times b raised to the x. Okay, and then you might want to add sliders. So just hit all for both a and b. You can set up your sliders to, let's see here, we can go from, for a, you might want to go from, let's say 0 to, say, 8. And you can adjust your steps to 0.1. And for b, you can go from, let's say, 0 to, well, we don't want to go too high. Let's go 0 to 10. And we can adjust that by 0.5 if we wanted to, right? And then you can play around with it, right? So let's graph that. Okay, so y equals a times b to the x. Oh, we're just going to have to graph this here. There it is, right? And you can see that what happens as you adjust a is the y-intercept changes. And as you adjust b, it changes the curvature and how steeply the curve increases, right? If you go down to 0, it's flat, right? So you might want to play around with that and see what you can discover about the exponential function.